Hey guys, this video is on mixtures of gases and Dalton's law of partial pressures. So when you have a mixture of gases, you can think about it as each of those gases being there independent of the others and then mixing them together. So in terms of the pressure. So if we have, like, say, three gases here, all in the same size container, all at the same temperature. One's at 300 kilopascals, one's 600 kilopascals, another 450 pascals. If we mix, if we combine all these, that pressure of each of this gas into a container that's exactly the same size at exactly the same temperature, the total pressure in there is just the sum of these pressures right here. 300 plus 600 plus 1450 is 1350 kilopascals. Or we can say that the total pressure, P sub T, is equal to P sub A plus P sub B plus P sub C plus however many gases there are. So that idea right there, that is Dalton's law of partial pressures. And when we say partial pressures, let's go back here for a minute, guys. When we say partial pressures, so in this mixture over here, the pressure of the first gas, the 300 kilopascal one, the pressure that it exerts inside of this container here is, under the same conditions, is 300 kilopascals. That pressure is called the partial pressure of that gas. The partial pressure of the purple gas would be, in here, would be 600 kilopascals, and of the gold one, 450 kilopascals. So that's what we mean by partial pressures. Or a partial pressure is the pressure of a gas in a mixture, the pressure that a gas in a mixture would exert if it was in the same container at the same temperature by itself. Another picture of this, remember volume and temperature are constant. We have gas A, or gas 1, its pressure here is this. Gas 2, its pressure here is this. So, whatever these units are, 3 and a little less than, or 2 and a little less than 3. When we mix them together, same volume and same temperature, the total pressure would be little under 5. 2 plus little under 3 is little under 5. So this is Dalton's law of partial pressures, another way of stating it over here. It's just using a summation sign. This Greek letter sigma just means the sum. So the total pressure in a mixture of gases is equal to the sum of the partial pressures of the individual gases. That is Dalton's law of partial pressures. Now, in terms of mole fraction, we're going to talk about mole fraction for a bit here. So, first of all, mole fraction, that's this Greek letter chi. It's defined as being in a mixture of gases, which is what we're talking about, the moles of one of the gases divided by the total number of moles in that mixture. N of I over N T, the total number of moles. Now, if we have whatever gas, gas I, whatever it is, this is just an index. Using the ideal gas law, PV equals nRT, or N equals PV over RT. So N of I is equal to P sub I, the pressure of gas I, V RT. The total pressure in that mixture will be the total number of moles will be equal to the total pressure times V over RT. Now, if we take the ratio of the number of moles, we get the mole fraction, Ni over Nt. But if we substitute what they're equal to in terms of the ideal gas law, Pi V over RT over PT V over RT, everything in here cancels, guys, except for the pressures. And so what that tells us is that the mole fraction of gas I, which is Ni over Nt, is equal to the partial pressure of that gas over the total pressure. Okay, that's the useful result from this little derivation here. Or in other words, the way we usually use this, if we want to calculate the partial pressure of a gas in a mixture and we know the total pressure, if we can find the mole fraction of that gas, the mole fraction of that gas times the total pressure will be equal to the partial pressure of that gas. Because you see, in a mixture of gases, it's impossible to measure the pressure of just one of the gases, because they're in there doing what gases do. It's a mixture. But we can calculate it this way. It's basically Dalton's law of partial pressures. So here we go, little example. We have a cylinder, so the volume's not changing. It contains 49.59 grams of nitrogen gas and 32.44 grams of carbon dioxide gas at 23.8 Celsius. Total pressure is 8.19 atmospheres. We want to calculate the partial pressure of each gas in the cylinder. So first of all, the temperature, you're just told the temperature so that you know that the temperature stays constant. That's all. You don't use it in the actual calculations. It's going to be what we just saw a minute ago. So why don't you guys go ahead and do this calculation. When you get an answer, come on back. Welcome back. All right, so first of all, okay, we know that the mole fraction of nitrogen, remember it's N2, it's a diatomic Hofbrinkel. It's the partial pressure of nitrogen over the total pressure, or the partial pressure of nitrogen, which is what we want, is equal to the mole fraction of nitrogen times the total pressure. And the mole fraction of nitrogen, definition, the moles of nitrogen over the total moles. Same thing for carbon dioxide. Partial pressure of carbon dioxide will be equal to the mole fraction of carbon dioxide times the total pressure, and the mole fraction of carbon dioxide, just the moles of carbon dioxide divided by the total number of moles. So you guys, the first thing we do is we calculate from the masses that were given the moles of each of the gases. So the mass of the nitrogen divided by its molar mass gives us the moles of nitrogen. Likewise, the mass of the carbon dioxide divided by its molar mass is the moles of carbon dioxide. Add those two up, and that gets us the total number of moles, N sub T. So now we know enough to calculate the mole fraction of each of the gases. We were given the total pressure in the problem, so we just plug in up here and get our answer. So let's do that. Let's get the mole fractions. So the mole fraction of nitrogen is just the moles of nitrogen over the total moles, which is 0.7060. Mole fraction of carbon dioxide is 0.2939. Now notice something, because there are only two gases, the mole fractions must add up to 1. So we could have, once we got the mole fraction of one of these, taken 1 minus this number, and we would have gotten the same answer. We're given the total pressure in the problem, so now that we know the mole fractions, we can calculate the partial pressures. Partial pressure of nitrogen, mole fraction of that nitrogen times the total pressure is 5.782 or so atmospheres. Likewise, partial pressure of carbon dioxide, mole fraction, total pressure, 2.407 atmospheres. Also, just like we could do with the mole fractions, guys, because there are only two gases in here, we know that the sum of their partial pressures must equal the total pressure. That's Dalton's law of partial pressures. So once we found the first one, we could have just subtracted the 5.782 from 8.19, and that would have given us the mole fraction, the partial pressure of carbon dioxide. All right, so that's that. Next, collected over water. A lot of times chemical reactions occur in aqueous solutions, and if a gas is one of the products, sometimes, quite often, it's useful to collect that gas, to trap it, and take measurements of it to give us information about the reaction that's occurring. This is a real simple schematic of how you might, there's different ways to do this, how you might collect the gas that's produced in a chemical reaction. So what you would do over here, so this is an Erlenmeyer flask here, chemical reactions going on in here, and a gas is one of the products. So it comes up through here, this is a glass tube in here, under here, this is a bent glass piece of tubing. Now this upside down Erlenmeyer flask here, the collection flask, what we do is we start out, we fill it all the way full of water, and put something over it like a piece of glass or metal, and then invert it and put it down into this container of water. Then pull off the piece of glass or metal or whatever we closed it with. So we start out with this guy here full of water submersed in this container of water here. Then when the chemical reaction occurs, the gas that's produced comes over here, up into here, pushes the water out. Now, if at the end of the experiment we make sure the level of the water, by moving the collection flask up and down, make sure the level of the water that's left in here is equal to the level of the water in here, then we know that the pressure inside of this flask, the pressure of that gas that was from the chemical reaction, is equal to the atmospheric pressure, which we can measure easily just by reading a barometer. But the thing is, it was collected over water, which means that some of these water molecules vaporize and they go up in the gas phase. So what we have up here inside this collection flask is a mixture of gases. The gas that was produced by the chemical reaction plus water vapor. So first of all, if you ever come across a problem, which you will, where it says collected over water, that means this is the scenario we're talking about. And because what we can measure is the pressure, the atmospheric pressure, And what we need, though, for our calculations is going to be the pressure of the gas inside of this collection flask, which is the gas that was given off in the chemical reaction. If we can look up the pressure of water, which is called the vapor pressure of water, we can just, take the atmospheric pressure that we measure, subtract the vapor pressure of water, and that'll give us what we need. This table over here, you don't have to write this down or memorize or anything like that. But what this is, it's a table where the vapor pressure of water is tabulated versus temperature, because it changes. The higher the temperature, the higher the vapor pressure of water. So, for example, let's say the temperature of the gas was inside this flask was 37.3 degrees Celsius. So to read this chart, you read to the ones place in the left-hand column and the tens place in the top row. And where that row and column intersect, that's the vapor pressure of water in millimeters of mercury. So if the temperature was 37.3 degrees Celsius, the vapor pressure of water is 47.7 millimeters of mercury. Now I got these numbers by using what's called the Antoine equation. So these are calculated, and they're pretty close. They do a pretty good job. All right. So collected over water. Let's do an example. So we want to know how many grams of zinc reacted according to the following equation, which are given here, a balanced chemical equation. If we collect this many liters of hydrogen gas, 2.12 liters, that's at 30 Celsius, and the atmospheric pressure is 765.4 torr. So the basic approach is that from the balanced equation, we see it's a 1-to-1 mole ratio between zinc and hydrogen. We want to know the mass of zinc. If we can get the moles of zinc, we can use the molar mass to get the mass of zinc. Well, because it's a 1-to-1 mole ratio, if we can find out how many moles of hydrogen gas are given off, now we know moles of zinc, we can get the grams of zinc. So to get the moles of hydrogen gas, we're going to use the ideal gas law. PV equals nRT, or N equals PV over RT, because you're given pressure, volume, and temperature. The only catch, guys, is that this is collected over water. You're not even told that it's collected over water, but because this is an aqueous solution, it had to be. There's no way to collect it dry. So because the hydrogen gas was collected over water, you're going to have to use this table and find the vapor pressure of water, and use Dalton's law of partial pressures to find the pressure of hydrogen gas by itself. So why don't you guys go ahead and work this out, and when you get an answer, come on back. Welcome back. All right. So moles of zinc is equal to moles of hydrogen. We can get the moles of hydrogen from the ideal gas law, N equals PV over RT. First thing we're going to do is take that atmospheric pressure we're given and subtract out the vapor pressure of water at 30.0 Celsius, because that was the temperature we're given. And so this 31.7 here, guys, I got this from the table. Now, the table's millimeters of mercury, these are torr, but remember, torr and millimeters of mercury are essentially the same. So we can just substitute one for the other. So we subtract out the vapor pressure of water from that table, from the atmospheric pressure given. That gives us the pressure of the hydrogen gas, which is what we need for the ideal gas law. The volume we were given, temperature we were given in Celsius, so we must convert it to Kelvin for the ideal gas law. And I'm going to use 62.36 liters torr per Kelvin mole for R, because we have torrs. So plugging into the ideal gas law, PV over RT, we get the moles of hydrogen, 0.08227, which is equal to the moles of zinc. So now that we know the moles of zinc, all we have to do is multiply by the molar mass of zinc to get the answer, 5.38 grams of zinc. And that's all there is to it, guys.